Now, another approach to determining the response of a system to forcing is the transfer function approach, which is a very helpful tool to simulate the response. First, let's examine the equation of motion of a general single degree freedom system under force f of t. Now, I will convert this model to a transfer function using Laplace transform. Now, in Laplace transform, when we are talking about transfer functions, we assume that all initial conditions are zero. Assume zero initial conditions, which means that now the Laplace of x of t is x of s, and the Laplace of the derivative x dot of t is only s x of s. Now, generally, there's the initial conditions minus x of 0, but since we assume all initial conditions in the case of transfer functions to be 0, this will be the only term for the first derivative, and for the second derivative, x double dot of t will be s squared x of s. And of course, the Laplace of any function in time is the function is itself in frequency range, frequency domain f s. So now substituting these into the equation of motion, taking the Laplace of the complete equation of motion, I would have m s squared x of s plus c s x of s plus k x of s equals f of s. Now the transfer function is defined as the output divided by the input. The transfer function, it's called g of s, is output divided by input, which is in our case the input is the force and the output is the displacement. So the transfer function becomes 1 over s m s squared plus c s plus k. For this transfer function, as a plot diagram, I can represent it as g of s. The input is f, the output is x. Now this is very helpful in MATLAB Simulink. You can build a simple model, simply use the transfer function block which is in the library under continuous systems. You'll find the transfer function block, and you can use any input. For example, for sinusoidal excitation, you can use a sine block which you can find under sources, and you output the output of the transfer function. You can send it either to a scope, which you can find it under sinks, or you can output it to data files or to the workspace. Now you can use a sine wave, and you can use any kind of input. You can use constant input, sine wave, ramp, step input, sky's the limit. You can choose, and you can also use a signal builder to build a regular shaped force and input it to the system. It's straightforward. Now if you open the dialog box of the transfer function, it will ask you for the numerator and the denominator, the coefficients. Basically you have a box in here and another box in here. Now the numerator, the coefficient is 1, and for the denominator the coefficients are m, c, k. Okay. So of course you'll have numbers for those, m, c, and k square brackets. Now this, when you input this, it will appear here as 1 m, whatever the number is, s squared plus cs plus k. Now pay attention to something, that you have to input all the orders of s. For example, if your system is undamped and you only have a transfer function of 1 over m s squared plus k, that's when the damping is 0, what you input here is not m, k. This is wrong because it will show you 1 m s plus k. What you should do is actually input m 0 k. You have to have all the orders of s. This is s power 0, s power 1, s power 2. So you can have any kind of input to the transfer function, run the simulation, you get the output on a scope. Another helpful application of this transfer function is the case of the base excitation. In the case of base excitation, the equation of motion was mx double dot plus cx dot plus kx equals cy dot plus ky. Now if I take the Laplace of both sides, I'll get m s squared x plus cs x plus k x equals c. Now the Laplace of y dot, just like x dot is sx, it's s y of s plus k y of s. Now here the transfer function g is the output x divided by the input, in this case y. So the transfer function becomes cs plus k over m s squared plus cs plus k. And here's your other transfer function that you can also input in the transfer function block, and have whatever profile you want for your base excitation, whether sinusoidal excitation or any other shape, ramp, step, or you can build your own random signal using signal builder. That's very helpful block. Now the transfer function goes up here. Now the output to scope, or you can output the output here, send it to a data file, or you can send it to the workplace or workspace of MATLAB, and then read the data in the workspace and plot whatever figures you want to do, whatever output you want to display in graphical format. So it's a very basic and straightforward approach for simulating the response of any single degree of freedom system, whether damped or undamped, to any input, whether force, whether displacement. And of course, if the input is due to rotating unbalance, simply the amplitude of the sine wave should reflect the m omega b squared e. This will be the f, which is the amplitude of the sine wave, instead of f0, the straightforward amplitude for sinusoidal or harmonic excitation.